Let's continue with chapter 30. So here is chapter 30 is focused on Faraday's law, right? And we have been working with Faraday's law, the EMF end of it, the EMF side of it. We haven't calculated the electric field yet, but we will do so today. And, so the plan for today is to try to finish this chapter. Maybe some stuff will drag on to Tuesday, but my goal is to hopefully finish. That's it. So here's an example. It says here a 2 centimeter loop of wire. So it's a wire loop, not just a mathematical loop, an actual loop, with resistance of 0.01 ohms is placed at the center of a solenoid. So you have a solenoid, and within that solenoid, there is a loop. So here is a, let's say here is a solenoid, like so. And within the solenoid, you place a loop, okay? So there is a loop within the solenoid. Can you imagine that? So the solenoid, and it has a loop within. Okay. So, I mean, obviously, if the loop has 2 centimeter diameter, the solenoid has to be a little bit wider, right? So for the loop to fit within the solenoid. Does that make sense? Okay. So, okay, and they say the solenoid is 4 centimeters in diameter. So it will fit within it, right? So the loop is 2, this one is 4, so everything is fine. So good. Now the solenoid is 4 centimeters in diameter, 20 centimeters long. So the length of the solenoid is 20 centimeters, and it has N turns per meter. Yeah.
Just on short, so the loop, is it 2 centimeters in circumference, or is that like the radius or the diameter?
In diameter.
In diameter, okay.
I missed the word diameter. A 2 centimeter diameter. Okay, diameter. I think it's diameter, not radius. Yeah, diameter. I forgot the word. Any other questions? So you got a loop within a solenoid. Okay. So, if you want the side view of this, the solenoid will have, let's say, the current on the solenoid will look like this. This is just a slice of the solenoid, this way. And the current comes in, comes out, comes out, comes in, comes out, comes in, comes out, comes in, and so on. Right? Something like that. Okay. So, in what direction is the magnetic field within this solenoid? Right. It will be to the right. How do I know that? Well, here is a current. Just follow this current. The magnetic field will go like that, and for this one it will go like that, and for this one it goes like that, and for this one it will go like this. And so all of them are this way. Within a solenoid, the magnetic field is uniform, ideal solenoid, and it's along the axis of the solenoid, so right or left. So it's to the right. So the magnetic field is this way. Now, there is a loop here through which the magnetic field is entered. Okay. So the loop is like this. Okay. So the magnetic field is going through the loop. Okay. So let's first figure out what the magnetic field within this solenoid is. We know that for a solenoid, the magnetic field is B equals to mu naught times N times the current, right? Times the current in the solenoid. Mu naught is mu naught. N is, N. It's this thing, 1,000. And the current is the current in the solenoid. Now the current in the solenoid is changing. You see, it's given here. It starts at 0 and grows, and then it flattens. It becomes constant again. Okay. Now, let's figure out, because they want to know what is the what's the current in the wire loop. what would the induced current in this wire loop be? If the magnetic field is constant, the flux would be constant, and there would be nothing induced. If the current is changing, the magnetic field will change, which means the flux will change. And if the flux changes, there will be an induced EMF, which induces a current, right? So the flux is the magnetic field times the area. In here, magnetic field is uniform. The area is facing the magnetic field, so just P times A. Okay. So the flux will equal to mu naught times N times pi r squared times R, right? This is the area. I put the area before the current. Okay. So that's the flux. Now, the EMF, the magnitude of the EMF, forget about the minus sign. Technically, it's minus d phi dt, right? D phi dt. We're worried just about the induced current. We can figure out the direction, whether it's clockwise or counterclockwise, using lenses now. So for now, let's just, don't worry about the minus sign. Okay, so I'm just talking absolute value. So that derivative, mu naught is a constant, little n is a constant, pi and r squared are all constants. Only the current is changing. So it's equal to mu naught times little n times pi times r squared times di dt. Okay. So let's calculate this EMF, induced EMF. So the mu naught is 4 pi times 10 to the minus 7. The number here, n, is 1,000. So 1,000. Or 10 to the 3. That's 1,000. Pi is pi. And then r squared, the radius squared. The radius of the loop. So the loop has a diameter of 2 centimeters. Therefore, it has a radius of 1 centimeter, which is 1 times 10 to the minus 2, right? So 10 to the minus 2 for the radius. So 10 to the minus 2. But you need to square it because it's r squared. Now di dt. What's the derivative of the current? Well, during the increasing linearly, the derivative is the slope. Derivative is the slope. So what's the slope of this line? Well, it's the rise over the run. The rise is 10, the run is 1. So seconds, amperes, so it's 10. 10 over 1 is 10, right? So the slope is 10. The IDT is actually 10. 10 amperes per second. So 10. So let's calculate this induced EMF. I need some help with this. So I'll give you a moment to do it. So 10 to the minus 2 to the 2 is 10 to the minus 4, but times 10, that's 10 to the minus 3, times 10 to the positive 3. So all these things just cancel, so you don't need to plug in your calculator. So all you have is the 4 pi times 10 to the minus 7. 5 times pi is about 10, so you get about 40. 40 times 10 to the minus 7, so you get 4 times 10 to the minus 6 approximately.
Yeah,
How much do you get?
3.95 times 10 to the negative 6.
Times 10 to the minus 6. Thank you. Volts, right? Okay. Therefore, the induced current, I induced, will be the EMF over the resistance, Ohm's law, right? V over R. So you got 3.95 times 10 to the minus. Did we say minus 6?
Yeah.
Okay. And then the resistance of this is 0.01. So 0.01. So you got 3.95 times 10 to the minus 4 amperes. So let's see if I have it right. Now I have 1.97 times 10 to the minus 3.
I got 3.95 as well.
Okay. Am I missing something in the formula here? I have, let me just check in my notes. Mu naught, little n times the area of the IDT. Yeah. Okay, well, that's what we get. Alright, that's the number. I suspect I made a mistake here, but yeah.
I don't get how we cancel out all these things.
You can double check, 10 to the minus 2 to the minus, to the 2 is 10 to the minus 4. Times 10, that becomes 10 to the minus 3. And 10 to the minus 3 times 10 to the plus 3 would be 1.
Oh.
So they just go away.
Yeah, even when you cancel it out, and you
Yeah.
just do mu naught,
Okay.
yeah, I'm still just getting like 3.95.
Okay, then double check those numbers later, okay? Unless I forget a term here, something. Okay, anyways, I see Brian, you're looking at it.
I understand what they mean.
Oh, okay. Yes.
Why do you pick for the current? Why do you pick only like the first second rather than like the second for the entire graph?
Oh, yeah, so this current here, the induced current, there will be an induced current while the current is increasing. Afterwards, the current will just be constant. Afterwards, the current will be 0. So if you were to write the induced current, will equal to this. 3.95 times 10 to the minus 4 amperes for the time between 0 and 1. And then it's 0 for t greater than 1. Yeah. So from here to here, it's increasing,
Oh, okay.
therefore the flux is changing. Beyond that, it's 0.
So when you say the induced current, does you mean like the change in the current?
The current in this loop.
Okay.
So you have a loop in a magnetic field. So there is flux through the loop, right? And so since there is flux, and the flux is changing, Faraday's law says there will be an induced current. And the induced current will be calculated in accordance to Faraday's law. Yes.
This current is due to like an induced electric field that causes a change in difference in potential. Right?
Yes, yes.
Okay.
Yes, and we have not discussed the induced electric field yet. And within about 10 minutes we will discuss that, yeah. But that is the idea. Yeah.
Is the magnetic field outside the solenoid, like the top right, is that given?
Here.
Right one? Like the,
Here.
yeah.
Uh-huh.
Is the magnetic field like, or like given?
Yeah, it's a solenoid, so we know its magnetic field is mu naught and times I.
Oh, I'm sorry, I mean like the direction, like,
Oh, we have
How-
to figure it.
how do you figure it from like the words given? Like how
Well,
it comes out at
Oh,
the
I
top?
see. They told me there was a solenoid and it has a certain current, right? I just assumed it has this configuration.
Okay,
So it has to go either like this, or maybe it's coming from there.
but doesn't matter, or I guess it doesn't matter when you're like calculating it.
It does not, right? We're just
Okay.
looking for just magnitude.
Okay.
I think I saw another hand. Yeah.
I think I figured out why we got the wrong data.
Yeah.
For n, it should be 1,000 over the length of the solenoid. Because the problem in the book says it has 1,000 turns, not 1,000 turns.
Okay, thank you.
Yeah.
So, okay, so with these numbers though, we're correct.
Yeah, with those numbers you're correct, but the n value is wrong.
Okay, got it,
Yeah.
yes. So in the book, she's saying, the book says it's 1,000 turns, not per meter, per 20 centimeters. So that's the reason. Okay. So we have it right actually. With these numbers, it's correct. Okay. So, all right. There is a problem or any other, I think G had a question.
No, no, about the direction of the induced current, I guess we're gonna talk about that.
Okay, yeah, so, yeah, we can talk about the direction of the induced current. So, the magnetic, so let's say with this picture, right, with this picture, that doesn't hurt. The magnetic field is this way, and it's increasing or decreasing as the current increases?
Increasing?
Increasing, so the flux is this way and getting larger. So we need to oppose it by producing a magnetic field this way. So how do I produce a magnetic field that's that way?
Clockwise,
Running a current this way or this way?
this way.
This
It's viewed
way.
from this side.
Yes, towards, yes. So the current will be like this, counterclockwise as I feel it, from my view. All right, so the next one I touched on, it was power generators. So I'm just going to mention it qualitatively, and then we will get to induced fields. So there are different ways to generate power. One way, remember you had a loop, and there is a magnetic field. You take the loop and enter the magnetic field, keep running. That's one way to generate an electric current, right? Remember this one? If you have a magnetic field, let's say in this area, magnetic field in this area, this chalk is not easily erasable. So there is a magnetic field this way, and you take a loop here and you run. As you're running, as you enter, the flux increases, and so you want to oppose it, and so a current will run. And as you exit, a current will also run because the flux is decreasing. So you can generate a current that way. But that's not very plausible, right? Because, I mean, how long should the loop be? And how long will you run? So that's not very plausible. The other one would be take a bar magnet and run with it. You run with the bar magnet. Leave the loop alone and run with the bar magnet. That's also not very plausible because you require too much space. Okay? Too much space. You have to keep running, and running from where? Miles and miles? So that's not very plausible. Here's a better idea. So take a magnet like this. This is the north pole, and take another one. Here is the south pole of that magnet. Okay? All right? So that's that. Now, take a loop. Take your loop and orient your loop like this. That's it. In a certain direction. And the loop is like this on purpose. So now, there is a magnetic field from north to south. That's the magnetic field. Right, so let's say the magnetic field is coming from that wall to this wall, right? And suppose this is my loop. So the flux is maximum now, right? All the magnetic field is coming this way. Now take your loop and start spinning it. Start rotating your loop. As you rotate the loop, the flux becomes this. Flux, remember what it is? It's the magnetic field times the area, right? But times the cosine of theta. Cosine of theta. Because if theta is 0, there is maximum flux. When the magnetic field and the area are facing one another, you got maximum flux. But this way, how much magnetic field goes through here?
0.
0. Yeah, I'm assuming the loop is pretty thin. So 0. So when the angle, now the area, let's say it's going this way, the magnetic field is this way, so they make a 90-degree angle, so it's 0. So, but if you keep rotating, the angle keeps changing and the flux will keep changing. So suppose you're rotating it at a certain rate, angular velocity omega, at a certain angular velocity omega, And remember what omega is, it's d theta dt, the rate of change of theta. So theta would be omega t, if omega is constant. So you got V is equal to B times A times the cosine of omega times t. You're constantly spinning this thing. Okay? As you spin it, there would be an induced current. The current will not run in the same direction. Sometimes it will run clockwise, sometimes counterclockwise, depending on how the flux is changing. But nevertheless, you'll always have a current. Or most of the time you will have a current. There will be, we will see what the current is. Let's say, Faraday's law would say then, d phi dt, right, magnetic flux, or minus d phi dt, if you want. Derivative of cosine is minus sine, and omega will come out, right, from the chain rule. So you basically get the magnetic field times the area times omega times the sine of omega times t, and therefore the current is equal to, well, it depends on the resistance that you have. So the current would be this over the resistance, and so you get BAW over R times the sine of omega times t. So you will have an alternating current. You see the current is sinusoidal, or a cosine if you want, sine, cosine. It's a regular function. So it changes regularly, according to the sine wave, let's say. And it's zero sometimes, right? It's zero when omega t is equal to 0, or pi, or 2 pi, or 3 pi, or 4 pi, and so on. Otherwise, it's not 0. And on average, it will not be, on average, if you want to calculate the power, there would be an average power. And the power would be I squared times R, right? I squared times R. So you will be squaring the sine, so you get sine squared. And the average of sine squared over a cycle is a half. Cosine squared plus sine squared is what? 1. So the sine will take half the average. So 1/2. Anyways, that's how you generate an AC current. Okay. So this is a better generator than the one where you're running. This one, it doesn't require space. You just need to spin something. And who spins it? Well, you can spin it. Take a crank and just keep doing this. We actually have light bulb where you just keep cranking something mechanically, and it will turn. And as it turns, a light bulb will light. But it will light only as long as you keep turning. And then, as soon as you stop, it will stop. So if you have wind power, or somebody who keeps spinning it, then it will keep running. And if you have a way to store that energy, then when you stop, then you can let the energy go through again. Okay. So, anyways, this is an AC. Okay. Any questions on the AC current? That's in principle how a generator works. Obviously, this is really oversimplified. There is more technology to that, but that's the basic. Something is spinning, always. Something is rotating. Somebody has to rotate something. Okay. Now, to increase the energy or to increase the current, what do you have to do? Think about it.
Alternating current.
Magnetic field is fixed, right? You can use a bigger area, right? You can use a bigger area. Resistance, you can't really do much about it. It's, people they have their light bulbs, their computers, their hair dryers, their whatever. So this one is also depends on the consumption. So increase the area, or instead of having one loop, well, have 10,000 loops. Okay, 10,000 loops. Or spin faster. Right? If omega is larger, you get a larger omega here, so you get a larger current. Okay, so I will go on. Now the induced fields. Okay, let's see. So I'll go to this board. Okay. So induced fields, we talked about the induced EMF. And For this case, we were able to explain the current. For this case, when the loop is being dragged at a certain velocity, we were able to explain the current using what? How did we explain the current with this one? If there is a velocity, did we need Faraday's law? Remember? Did we need Faraday's law? Remember we said every piece of the wire will have a certain velocity to the right, and if the velocity is to the right, the magnetic field is N, and so there will be a velocity this way, or a force this way. It was Q, V plus B, right? And if there is a force this way, it means the current is that. So we were able to explain the induced current using this force law. However, if the magnetic field itself is the one changing, well, let's say the current loop is fixed, not moving, but you're bringing in a magnet closer. Well, the loop is not moving, so you can't really say it's the velocity. Velocity is zero. So who is responsible for making that current increase? So let me do it again. So here is a loop. This is a wire, okay? A wire loop. And let's say the magnetic field is N, okay? Magnetic field is N and increasing. Increase in magnetic field. So the magnetic field is into the board and getting larger. In what direction will the induced current be? Counterclockwise. Yes. So does everybody follow that? So because the magnetic field is N, the flux is N, and it's getting larger. So you want to oppose it or go with it? Always oppose. If you want to oppose it, it's getting larger. Well, we need to oppose it by producing some magnetic field this way. How do I produce a magnetic field this way? Clockwise or counterclockwise? Well,
Counterclockwise.
Yeah, counterclockwise, just put your thumb along the clockwise direction and the magnetic field will come out. So the magnetic field will be out if it's counterclockwise. So in this case, the induced current will go like this. Now, who is pushing the charges in this circular map? Not the V. It's not this QVB, right?
Electric field.
There has to be an electric field. Well, how do I know that? Well, we have in electricity and magnet, well, Newton's laws say you need a force, right, for things to start moving, to accelerate. So we only know of two forces. You got the magnetic and the electric force. Now, if you can't explain it with either, then you have to come up with a new theory and say, maybe there is a new force that we don't know. But fortunately, the electric force explains it, and so no need to modify the theory. So it is the electric field that is pushing the charge. So charges respond to electric forces and magnetic forces. So it has to be this electric field that is in the counterclockwise direction. Now, this is a physical loop, a wire loop. What if I remove the wire loop? So here is now a magnetic field, and it's increasing. There is no current, because there are no charges, right? But does it mean there is no electric field now? So there is still an electric field. It's in the counterclockwise direction still, although there is no loop to experience that electric field. If you were to place a loop there, there will be a current. So the direction of the electric field will be counterclockwise. So to determine the direction of the induced electric field, think about what happens when you put a loop there, a physical loop. What happens? Okay? And so this is the left side now of Faraday's law. Basically says the integral of E dot ds is equal to minus ddt of this magnetic flux, of the magnetic flux. All right. So that is that's the diff. And we have been saying that's the induced EMF. We bypass the electric field. So now the question is, how do I get that electric field itself? How do I calculate the electric field? Well, this is the equation, and if there is symmetry, we'll take advantage of it. So let's do 2 more examples of this. let the magnetic field be out. Let's say the magnetic field is out. Here's the magnetic field, it's out, and it's increasing. So the magnetic field is out towards you, and it's getting larger. So in what direction is the electric field? Before you answer, I want you to maybe talk to your neighbor first, and then for about 30 seconds. So think about it, 30 seconds, and then no. So magnetic field is out and getting larger. Question is, in what direction is the electric field? You have two options, clockwise or counterclockwise. Give you
Yeah. But I believe it's
It's really good, what?
Oh, you.
So, alright, so let me try to get an answer maybe on that side of the room. Clockwise. Clockwise? I agree. Be clockwise. Why? I heard they said it just be the opposite of this. That's true. I mean, a magnetic field going in, well, just go to the other side of the board and look at this same magnetic field will be coming towards you and increasing, right? But I don't want you to think about it, well, in addition to thinking about it that way. That's a good way to think about it. Let's think about the flux. Coming towards you and getting larger. You need to oppose it. You need to produce some flux this way. How do you do that? By running a current this way, if you were to have a loop. Well, in the absence of a loop, there is just the electric field that's electric field. This is the E.
Do you know if they proved this by mathematics or by just tests?
That is actually a physical law that you can't just use logic to prove it. You have to do experiments to prove it. You can guess it, but then you have to verify the experiment. Oh, good. So there are some laws that all physical laws, at the end, it's physics, and it's an experimental science, and you have to verify it experimentally. Otherwise, it remains just a hypothesis, right? And then finally, if you want the fourth option, so let's say the magnetic field is coming towards you and decreasing B, then in this case it would be counter, right? Counterclockwise. Well, here is one more. Let's see if you understand it. So here is the magnetic field. It's coming towards you. B is constant. In what direction is the electric field?
There is no
electric field. Good. How do I know? Well,
change in magnetic flux.
that's zero. Yeah, there is no change. Right side is zero, so no electric. Okay. So let us try to get some calculation. Suppose we have a solenoid, and I'm going to try to copy it correctly this time so I don't make an error with the numbers. For example, suppose you have a 4 centimeter diameter. Example, you have a 4.0 centimeter diameter solenoid with, this time I think I'm right, it's 2,000 turns per meter, yeah, so with N equals to 2,000. 2,000 turns per beat. Alright, that's the solenoid. So if the diameter is 4 centimeters, obviously the radius of this solenoid is 2, right? Next is the current through the solenoid oscillates. The current through the solenoid oscillates at 60 hertz, meaning 60 cycles per second, with an amplitude. We'll see what all this means with an amplitude of 2 amperes. 2 amps. Okay? 2 amperes. What is the maximum strength of the induced electric field in the solenoid? What is the maximum induced field? By field I mean electric field. E field. So there will be an induced electric field, and the question is how much is it? How much is it going to be? So let's try to kind of unwind all this. Did they tell me that the solenoid looks like this? Well, it has to look like this, or maybe the opposite. There will be a solenoid that has a magnetic field in it, either running right or left, if my solenoid is oriented horizontal. Okay? So I'm going to take a side view of my solenoid. So here's the solenoid. You're looking at it this way. So you're looking at it this way. And suppose the magnetic field may be coming towards you or away from you. Okay? So here is the solenoid. This is the solenoid. This is a side view of the solenoid. And the magnetic field is either going towards you or going away from one of them. Okay? So we don't have to worry about which one. So there is a magnetic field either towards you or away from you, because the current is alternating. Sometimes it's going like this, or sometimes the current is actually running like that. So it depends on what the current is doing at the moment. Okay? And in this case, the current is alternating. It's an alternating. So going back to basically here, this is the current, and it alternates like this. Alternates like this. So let me write down the formula for the magnetic field inside the solenoid. B inside the solenoid is mu naught times little n times the current, right? Times the current. And so this becomes mu naught times little n times I0 times the sine of omega times